Welcome to the Predictive Analytics for Marketing course. My name is Dr. Ash Pava, and this is lesson 3. Here we are discussing relationship and distributions. So in the previous lesson 3.1, we covered covariance and correlation. After that, we covered rank and partial correlation in lesson 3.2. So now this is lesson 3.3, in which we will discuss the normal distribution. As you recall that we covered this topic of normal distribution briefly in lesson 2.3, which was numerically summarizing the data. So this lesson 3.3 is a continuation of the lesson 2.3. So there are certain portions of this lesson 3.3 are similar to the lesson 2.3. But a few things which are new here, which is testing normality, which is at the end of this lesson and which is very, very important. Let us start with the lesson outline. First, we will define the distributions. There are many different types of distributions. In this course, we are going to examine the uniform distribution and also the normal distribution. The focus of this lesson, however, is a normal distribution. Next, we will define the probability distribution function, which is the relative frequency histogram. As you may recall, we have already covered this type of histograms. Then we are going to very briefly examine the uniform distributions, but we will focus primarily on normal distribution. Next, we will explore a standard normal distribution. In the case of a standard normal distribution, it is a normal distribution with the mu is equal to 0 and sigma equal to 1. Finally, we will develop a test by which we can determine whether our data is really normally distributed or not. This test is a very important concept because in statistics, whenever we do procedures of any kind, we need to check whether the residuals are normally distributed or not. Such tests are very important and are used virtually all aspects of statistics. First of all, let us define distribution. Distribution is simply a histogram, which we covered in lesson 2. Now, based on some event, we may possibly have some sample space. Sample space refers to all possible samples that can occur for that particular event. So on the x-axis, we need to plot all the possible values of our sample, and the y-axis, we need to plot the frequency of our events. Therefore, the graph we draw is called distribution, and we are going to see a lot of examples of this distribution as we progress. Now let us take an example of distribution. Suppose we have a die that is one of the pair of dice, and we toss that die 10,000 times. In this case, the sample space is going to be 1, 2, 3, 4, 5, 6, because there are only 6 possible outcomes based on the design of the die. So when we roll the die, we are going to get either 1 or 2 or 3 or 4 or 5 or 6. We can assume that the frequency of these numbers appearing would be even. And if we do the simulation, we are going to find out that number 1 is going to appear 10,000 divided by 6 times, which is approximately 1,666. So as you will see in this distribution, all the numbers, which are 1, 2, 3, 4, 5, and 6, are appearing somewhere between 1,600 to 1,700 times. Because this is a random process, these numbers will not be exactly equal, but approximately equal. So on our y-axis, we have the frequency, and on our x-axis, we have the sample space. Plotting our data with this kind of a diagram gives us distribution. Now let us examine the distribution of our data. As you may recall, we used this data in lesson 2. Before we plot the distribution, however, let us one more time clarify the semantics of it. The table shows the number of arrivals at a restaurant within a 15-minute period. So let us explore this data in more detail. When the restaurant opens, 7 customers arrive during the first 15 minutes. During the next 15 minutes, 6 customers arrived, followed by another 6, and so on. So we have 40 total observations which have been displayed in this table. If we sort our data, we can see it in the table at the bottom of the slide. So as we look at the sorted data, we see that number 1 appears once. So once in 15-minute period, only one customer came. And how many times did 2 customers came in the 15-minute period? So we can count the number of 2's, which are 1, 2, 3, 4, 5, and 6. So in 6 15 minutes interval, there were only 2 customers who came, and so on. So this provides us with the semantics of this data. Now we are going to plot a histogram. In this case, our histogram will show a frequency or the count of how many times such an event has happened. We can determine how many times 7 customers came in the 15-minute period. So if we count this in the table to determine how many times number 7 appears, we see that number 7 appeared 5 times. Similarly, we can plot the frequency data of all values. So in the 15-minute time interval, how many times did only one customer arrive? This happened only once. And how many times did only 2 customers arrive? It happened 6 times. So we can count the number of 2's in this table. We can generate data which shows how many times a certain number of customers have come to the restaurant. Once we compute this information, we can plot it. Now we can see the histogram, and also we can compute the relative frequency. Remember, a relative frequency is the frequency of the individual divided by the total. Now, if we total these numbers, it comes out to be 40. So 1 divided by 40 would be the relative frequency of only one arrival. We can either plot the count or we can plot the relative frequency. Either way, the shape of the graph remains the same. As I said before, the advantage of plotting a relative frequency is that if we add all these numbers up, which are the relative frequencies, it comes out to be exactly 1. Therefore, relative frequency represents the probability of that event. In the previous slide, we were able to plot the relative frequency histogram. The relative frequency histogram is also called the probability distribution function. The area under the curve of the probability distribution function is always going to be the 1, and this probability distribution function is also called PDF. Next, let us define the uniform distribution function. When the probability of all possible events in a sample space is the same, then it becomes a uniform distribution. A classic example of this again is a die. When we toss a die, then the probability of all events are going to be the same. So there are 6 possible events that can happen. We are going to get either 1, 2, 3, 4, 5, or 6. So when the probability of all events is the same, we call this as uniform distribution. In the previous slide, we were able to plot the frequency when we tossed that die for 10,000 times. But if we divide all these numbers or frequencies by 10,000, we will get our PDF. So as I said before, one PDF property is that when we add all these numbers up, they will come out to be exactly 1. In the previous slide, we explored the uniform distribution. There are many different types of distributions, and we only saw one of them, which is the uniform distribution. The other distribution can be divided into 2 different categories. One is called the continuous distribution, another one is called the discrete distribution. So under continuous distribution, we have uniform, normal, chi-square, Fisher's F, student's T, gamma, exponential, beta, Cauchy, log, logistic, and Weibull. On the discrete side, we have binomial, Poisson, hypergeometric, negative binomial, and Wilcox. There are many other distributions, but the reason why we have different kinds of them is because the real world data will have different kind of distributions. For modeling purposes, we try to use the distribution which basically fits into the real world, because not all data is uniformly distributed or normally distributed. Some of the real world data have different kinds of patterns in it. So once we know what that pattern is, we can try to distribute those distributions in our statistical software in that way. We have discussed the uniform distribution. Next, we are going to focus on the normal distribution. Normal distribution is the foundation of statistics. In the case of normal distribution, we are going to see that most of the data stays in the center. But we are going to get a few exceptions which are on the right or the left hand side. Now let us take a real world example. Suppose we are trying to measure the height of people. The mean height of men in America is 5 feet 11 inches. So we can predict that most of the people we are going to find will be of that height or a few inches less or more. That means most of the people are going to fall into the center. Now, of course, there are going to be a few people like the basketball players who are exceptionally tall. Naturally, they fall on the right hand side of the distribution. We also know that some of the people are very short. They, of course, are going to fall on the left hand side of the curve. So our curve basically shows the frequency, that how many people there are with these characteristics. Most of the real world data falls into the normal distribution, and that is the reason we study this particular distribution in detail. Empirical rule says that 68% of the data remains within one standard deviation, 95% of the data within two standard deviation, and 99.7% of the data remains within 3 standard deviation of our normal distribution. Now let us take another real world data example, which is the student IQ test. The student IQ test has a mean of 100 and a standard deviation of 15. That means that if we subtract 15 from 100, that gives us 85. And if we add 15 to 100, we get 115. So between 85 and 115, there will be 68% of the students. As we can see, 68% means that more than half of the students are going to fall within this range. That is the reason why we see this bell-shaped curve, where the frequency in the center is high, and of course a few people are going to be very intelligent with extremely high IQ. Similarly, a few people have a low IQ. So as we have learned, there are always going to be a few people who are going to fall on the extreme left or extreme right. So for these reasons, we study normal distribution. A lot of the real world data has this type of pattern. If we have to describe the normal distribution, we can do it in mathematics as the probability of x equal to 1 over sigma under root of 2 pi e to the power of minus x minus mu whole square divided by 2 sigma whole square. But we are not going to use this formula because there are a lot of tools available that can give us the distribution which is normal. As we see in the formula, mu is the mean and sigma is the standard deviation. Now we are going to increase the sigma, meaning we are going to increase the standard deviation. We notice that this particular shape is going to become very wide. So if our sigma is 1, we see it on the left graph that the normal distribution is very tall and also very narrow. Now if we increase our sigma from 1 to 2 and keep mu equal to 10, it means that our mean is 10. In that case, we see that the distribution is going to become a little bit wider. Also, if we increase the sigma to 3, as you can see, it's going to become wider still. So as the sigma increases, the graph widens. Now, if we increase the mean from 10 to 15, we will see on the right hand side that our distribution basically gets shifted. So on the left hand side, we see the mu is 10, and on the right hand side, we see the mu is 15. This normal distribution graph is being represented by this formula, and with it, we can graph the normal distribution. Now let us examine the properties of normal distribution. The first property is that it is symmetric about its mean, because in the center we have the mean, and in this distribution mean is equal to median, which is equal to the mode. That is because the mode is one set of data which has the highest frequency. It remains right in the center. So there always be a single peak at x equal to mu. The inflection point basically means that the slope of this particular graph is going to reach its peak at these two inflection points. And as we move from that inflection point, the slope will become less or more. Our inflection point is going to be at mu minus sigma and mu plus sigma. Finally, once they reach the top, slope becomes 0. So these two inflection points basically represents the place where the slope changes its direction. Then the blue area which we are looking at will be exactly 1. The area on the left hand side where we have x is less than mu is equal to the area on the right hand side where x is greater than mu. Empirical rule says that 68% of the data remains within one standard deviation, 95% of the data remains within 2 standard deviation, and 99.7% of the data remains within 3 standard deviations of our normal distribution. So these then are the basic properties of normal distribution. So far we have explored the normal distribution. Now let us move to another distribution which is called standard normal distribution. Now, as you recall that in lesson 2.3, that was the previous lesson, we covered this topic. So I'm going to cover this topic of the standard normal distribution one more time because of course it is related to normal distribution. So next 11 slides are based on the standard normal distribution, which is nothing but the same thing that we saw before in lesson 2.3. So if you choose to not to see these slides, next 11 slides, you can skip them and then you can go to the next topic, which is testing normality. So in the case of a standard normal distribution, as you recall that we assume that the mu, which is the mean value, is 0 and the standard deviation is 1. Now, one of the advantages of creating a standard normal distribution is that a lot of probability models can be very easily solved using the standard normal distribution. So now let us review the standard normal distribution. As I said before, the mu is 0 and sigma is 1. So when we take the normal distribution and these mu and sigma values, the normal distribution becomes the standard normal distribution. Again, in this case, mean is equal to the median is equal to the mode, which happens right in the center. The inflection points are at plus and minus 1. This is so because it's the place where the slope of the graph changes its direction. The area of course, under the graph is equal to 1, and the area on the left hand side of the mu is equal to 0 is the same as the area on the right hand side, of course, which is going to become half. And it follows the empirical rule, which states that 68% of the data is going to fall within one standard deviation. Since our standard deviation is 1, 68% of the data is going to fall from minus 1 to plus 1. 95% will range from minus 2 to plus 2, and 99.7% will range from minus 3 to plus 3 values. For the standard normal distribution, we have these tables, which are often provided in an appendix in most books about statistics. Although these tables are available, few people use them these days because in the tool sets we use on a daily basis, like Excel, R, or SAS, or any other statistical tools, they have a built-in functions to compute these numbers very easily. But if you don't have access to such tools, then you can always revert back to these tables. So this particular table gives you the z values, which is the horizontal axis, and then the area. Area is also called the p-values. So we can compute the p-values based on every z value from this table. Now let us compute the z value from Excel. As you know, Microsoft Excel is extensively used for statistics. We can use it for the functions available to us to compute the z values. This is the same data that we used before, the standard IQ test, with a mean of 100 and a standard deviation of 15. If our score is 110 and if you want to compute the z value, one way to do that is to use a formula, which is 110 minus 100 divided by 15. Or we can use the standardized function which is available to us in Excel. So we can, as we can see here in Excel, we are using the standardized function, which takes basically 3 arguments. The first one, of course, is B5. B5, as we can see, contains the actual data value. B2 is the mean, and B3 is the standard deviation. So we get the z value as 0.666. And again, if we compute the z value using the formula, which is 110 minus 100 divided by 15, we will get the same answer. And now suppose that the z value is already known to us. How can we compute the probability and the area? In this particular chart, suppose z value is 0.21. We are a little bit on the right hand side because when the z value is 0, we know that the area is exactly 0.5. So with our z value being 0.21, we look into the table found at the end of most of the statistics book. Or we can use, since we are using Excel, we simply can use the normal S distribution, and S stands for sample. So norm S dist, and if we feed in our z value, we are going to get the area. So as you can see, by feeding in the value of 0.21, we get the answer of 0.5832. So 0.5832 is the area which is shown here in red. As you can see, it is a little bit more than 50%, because 50% would have been exactly where the z value is 0, right at the center. In our example, we are a little bit on the right hand side, so the value of the area comes out to be 0.5832. So as you can see, this can be easily computed in Excel rather than going back to those tables to determine this value. Now suppose we need to compute the area on the right hand side of the z value of 0.21. To do that, we simply subtract from 1 the number that we got before. So if we compute 1 minus norm S dist function and feed in again the same value of 0.21, we are going to get 0.4168. As we can see, the previous number that we got was 0.5832. And if we subtract from 1 0.5832, we are going to get 0.4168. So this number 0.4168 then represents the probability that our variable is going to be greater than 0.21. We can of course determine the probability that the variable is going to have a value between two given values. So if we are given two values which are z1 and z2, and in this case we assume them to be 0.31 and minus 0.31. In Excel we can again use our normal distribution function. So first of all we will feed in B12. B12, as we can see, is plus 0.31, and then minus the normal distribution at B13, and B13 is minus 0.31. So this gives us a value of 0.2434. It is telling us that almost 1/4 of the data is going to fall in this region where the z-values are plus 0.31 and minus 0.31. So with our total probability as 0.2434, 1/4 of this entire data is going to fall within these two boundaries, where the z-values are 0.31 and minus 0.31. Now let us examine the inverse function. Earlier we were given the value of z and we were trying to find out the area. Suppose the area is given and we need to find out the z value. Excel provides a function which is called norm SINV, and INV stands for inverse. We are basically reversing the whole process. So as you may recall, when our z value is 0.21, the area which we are getting was approximately 0.58. Now if we feed 0.58 in the normal inverse function, of course we are going to get the z value as before. Which we are going to get would be 0.2019. So we can easily convert z value to the area and area to the z value. Excel provides useful tools by which we can compute these numbers. So here are the summary of the Excel functions that I have been explaining in the last few slides. So if you are given the value and if you know the mean and the standard deviation, you can use the Excel function called standardize and you are going to get the z value. Now from the z value, you can compute the p value by a function called norm sdist, which basically means normal standard distribution. And then from p value, if you want to get your z value back, then you use the inverse function, which is norm S inverse, normal standard inverse function. So this is just a summary of the functions that I talked about before. So you can get p value from z value and you can get the z value from p values. There is another package called R, which also has these given functions. So let us use R to compute these numbers, and our answers will be the same. Our mean is 100, and our standard deviation is 15, and the given data value is 110. First of all, we compute the z value, which comes out to be 0.666. Now, given the z value of 0.21, we can compute the area, and I can do that using the pnorm function. When we feed in 0.21, we get 0.5831. Similarly, I can also determine the area on the right hand side from the z value, which is going to be 1 minus pnorm. So we get the value of 0.4168. We can also compute the area between two given z values, which are minus 0.31 and plus 0.31. As before, we will use the same pnorm function and pnorm z2 minus pnorm z1. So we again get 0.2434, which is the same number that we got before. R also provides the inverse function, which is called qnorm. So in given area of 0.58, we can determine the value of z, which comes out to be 0.2018. And that is the same result that we saw before. So everything we previously did in Excel, we can do it in R. Since these functions are given to us in Excel and R, we have even less reason to use the tables printed in the back of all statistics books. But if you don't have access to these tools, then of course the book tables will be useful. So these are the functions that are used in R. If you are given the value and if you know the mean and the standard deviation, you can use the function scale to get the z value, and you can get the p value from z value using the pnorm function, and you can get the z value from p value using the qnorm function. So these are the functions that are available in R. So pnorm and qnorm are inverse of each other. And in fact, these are the functions that we have seen in R. No matter which statistical package that you use, you're always going to find similar functions by which you can compute the p-value from z-value and z-value from p-value. So far, we have defined normal distribution and also standard normal distribution. Now let us focus on another problem. Suppose a set of data has been given to us. How can we determine whether the data is normally distributed or not? In statistics, there are many occasions where we have to verify that the data that we have is normally distributed. So we are going to develop a test by which we can determine this. Many statistical inference procedures assume that we are sampling from a normally distributed population. So we need a way to test whether the data is really normal or not. A classic example for this one is the residuals that we get from regression. As you may recall from our previous lesson about regression, we learned that if a regression is good, it must have residuals that are normally distributed. This then is a problem that we need to solve. Since we know the histogram of normally distributed data will resemble a bell-shaped curve, one of the ways by which we can check whether the data is normally distributed or not is by creating a histogram of it. If the histogram resembles a bell curve, then we can assume the data is normally distributed. But the problem in this approach is that if we change the bin size, the shape of the histogram is going to change. Furthermore, we are never sure whether the histogram plotted has the right bin size or not. So for this reason, this particular technique does not work very well with the real-world data. Since the shape of the histogram changes as the bin size changes, we cannot depend only on the histogram. The question becomes how to check that data is normally distributed or not. So we need to develop another method by which we can achieve our goal. If you plot the data against a theoretical normal distribution, and if you see a straight line, then we can say that the data is normally distributed. This method is called QQPlot, which stands for quantile-quantile plot. On the x-axis, we are going to have the quantile data, which is the theoretical normal distribution. On the y-axis, we are going to have the sorted data. If we see a straight line, then we can say the data is normally distributed. In the next few slides, we are going to take a few examples where we will take some normally distributed data and then verify that it is indeed normally distributed. Suppose the data that is given to us is 3.89, 4.75, 6.33, all the way till 6.64. Now the question is it normally distributed? In order to know the answer, we will develop a test. The first step is to sort this data. Here we have 9 observations. So we will sort this data, and the top number will be 3.89 because it is the smallest number. The next highest number will be 4.75 and so forth, all the way till 7.90. Since we have 9 observations, we will divide our standard normal curve into n plus 1 portions. So since n in this case is 9, we are going to divide our standard normal distribution curve into 10 portions. Then we are going to take the z-value for each of these 10 portions. Next, we are going to plot these z-values on the x-axis and the sorted value on the y-axis to see if we have a straight line. If so, we can conclude that our data is indeed normally distributed. And that's what we are going to see in the next slide. Now let us compute the z-values. We do this by dividing our standard normal distribution curve into 10 parts. Since we have 9 observations, we are going to divide our curve into n plus 1, which gives us 10 parts. Each part represents 10% of the area. Next, we are going to compute the corresponding z-values. Finally, we will plot the z-values on the x-axis and the sorted data on the y-axis. If it comes out to be a straight line, then we can conclude that our data is normally distributed. And now let us compute the z-values using Excel. First of all, as you see over here is our data, then we have our sorted data. Since we have 9 observations, we are going to compute this variable, which is I over n plus 1, because we are trying to divide this entire standard normal curve into 10 portions. So when our value of I is 1, it means that this is the first of our observation. We are going to get 0.1 because I over n plus 1 comes out to be 0.1. N in this case is 9. So 1 over 9 plus 1, that is 1 over 10, which is going to become 10%. If our area is 10%, then what are the corresponding z values? As you recall that we covered this function, which is the inverse function, norm SINV, that gives us the z value when the area is known. Now suppose the area is 10% or 0.1, then the corresponding z value will become minus 1.28. Next, we will compute the z values for all the 10 portions of our standard normal curve. The standard normal curve now can be divided by the z values, which are minus 1.28, minus 0.84, minus 0.52, and so forth, all the way till 1.28. Finally, we will plot the sorted value on the y-axis and the z value that we have just computed on the x-axis. If our sorted data is normally distributed, then we are supposed to get a straight line. And if we see a straight line, then we can declare that our data is normally distributed. And we will see that in the next slide. Now here I have a QQplot, which is a quantile plot. On the x-axis, we see that theoretical z values, which is minus 1.28, all the way till plus 1.28. So the x-axis represents a normal distribution curve because I've taken these values and divided the normal distribution curve into 10 parts. My y-axis contains my sample data, which is sorted. As you can see, I have these values as 3.89, 4.75, and so forth all the way till 6.64. So this is the y-axis. If we plot these things, we get an approximate straight line. Of course, we will never going to get an exact straight line, just something close to it. And again, it's a very subjective decision whether you want to accept this as a straight line or not. There could be a lot of situations where you are not 100% sure and you need to decide whether to treat this thing as a straight line or not. This issue is subjective, but in this particular case, we can see that at least 4 or 5 values are coming straight on the line, and 1 or 2 of them are slightly diverted from it. So we can conclude it is normally distributed. Now to assess whether our system really works or not, I'm going to generate some already normally distributed data so we can be 100% certain. Then we will do a QQplot and see whether we get a straight line or not. So in my R code, I have generated 10 random numbers which are normally distributed with a mean of 5 and a standard deviation of 2. I have got 10 observations here. So when we plot this line, as you can see, it is not really not coming out to be exactly straight line. The reason for this is because the number of observations here are too few. So in the next slide, I'm going to increase my observations from 10 to 1000 and then see whether our QQplot really works or not. Now I'm generating 1000 points with a mean of 5 and a standard deviation of 2. And I'm 100% certain that this is normally distributed because it is being generated by a random number generator which generates normally distributed data. I plot the histogram of this data and you can see that it does look normal. It is a bell-shaped curve. Now let us try to use a QQplot to determine whether the data is normally distributed or not. We actually know that it is and we should see a straight line. As you can see, when I do a QQplot, we get a more or less of a straight line. As I said before, we are never going to get an exact straight line, but something very, very close. Now let us examine the data where we know for sure that it is not normally distributed, but it is uniformly distributed. So if I generate 1,000 samples, and as you can see, if I plot a histogram, we get a flat curve, which indicates that the data is normally distributed. Now, if I test my QQplot, we can see that it is not a straight line. We find that the data is kind of a curve on the top and also at the bottom. So this is a classic example. If you see a curve like this, you know for certain that the data is not normally distributed. This then is a way by which we can verify whether the data is normally distributed or not. So this brings us to the end of our lesson. Let me summarize what we have covered. First, we looked into the distributions. We defined what a distribution is. We explored the probability distribution functions. We focused primarily on the normal distribution, but just to see how it is different, we also explored uniform distribution. Then we explored the properties of normal distribution. After that, we covered standard normal distribution. In the standard normal distribution, we have mu is equal to 0. Mu means the mean, which is equal to 0, and sigma, which is the standard deviation, comes out to be 1. So if we assume these two things, the normal distribution becomes the standard normal distribution. In the end, we designed a test by which we can determine whether the data that has been given to us is normally distributed or not. Thank you. I will rejoin you in lesson 7.